I'm going to finish up the rest of 6.1 here and then possibly start 6.2 in this video. So we're on problem 6. It says that a jar contains 5 blue marbles and 5 green marbles. You randomly select marbles from the jar one at a time until you get a blue one. Let the random variable x represent the number of marbles obtained until one is blue. Okay, part A is x continuous, discrete or continuous. This would be discrete since the values would only be counting numbers. And in part B, they want us to state the values here. So we want the number of marbles until one is blue. Well, there's 5 blue and 5 green marbles in a jar, so maybe you select a blue one on the very first pull. Okay, or maybe you select a green one first and then a blue one second. So it took two attempts. Or maybe you select 2 green first and then on the third selection you get a blue one. Okay, or maybe you don't see a blue one until the fourth selection or the fifth selection. Okay, or it could be that maybe you select all 5 green marbles, and since there's only blue marbles left now in the jar, on the 6th marble selected it's going to be blue. So these counting number values would represent the values of the variable. Now suppose that this experiment is done 10 times. So you're going to select marbles from the jar one at a time until you get a blue one. And the following data represent the number of marbles obtained until one is blue in each of the 10 trials. Okay, so here's some numbers that I just kind of made up representing the number of marbles selected until one is blue. So we saw a blue one on the second marble selected. We'll put all the marbles back in the jar. On this next trial, we didn't see a blue one until the 4th marble selected. Put all the marbles back in the jar, etc. Okay, so we did this 10 times, and here's the 10 numbers representing when we first saw a blue marble selected. Part C, construct a probability distribution for the given data. Okay, so the values are going to go on one side, the probabilities go on the other side. The values are the counting numbers 1 through 6, and I'm creating this table here. We did not see a blue marble come up on the very first try, so there's a 0% chance of x being 1 for the data that we have. There were 2 2s, so 2 over 10 would be the probability of selecting 2 from this list. There was only 1 3, so 1 over 10 would be the probability that we saw a blue marble on the third marble selected. The probability that x is 4 would be 3 over 10, there's 3 4s. 2 over 10, there's 2 5s, and then 2 over 10, there's 2 6s there. Okay, so here's my probability distribution. Again, the probability rules are satisfied, right? Each probability is between 0 and 1, and when you add up the probability column, you should get 1. I've got my common denominator of 10. If you add the numerators, you would also get 10. 10 over 10 is 1. Okay, now part D, we want to compute the mean for the random variable x, and then we'll interpret the result. Well, the mean is just simply we're going to add up all these numbers and then divide by 10, right? And so I'm assuming a population mean here for this problem. And so I've added up all the 10 numbers and divided by 10, and I get 4.1. That's an exact, by the way. Okay, now what that means is that on the average we would expect 4.1 marbles to be selected until one is blue. Now remember that the mean is not a possible value, right? The values are just these counting numbers. The mean is the number that is going to balance all the data values on a scale. Okay, so it's likely not going to be a value that's listed there in most cases. Now what I'm doing here next is I'm showing kind of an algebraic manipulation of this formula here to be able to see how we can still get the mean from this distribution. Okay, it looks like if you just take the value times the probability, so I got 2 times 2 over 10, 3 times 1 over 10, 4 times 3 over 10, 5 times 2 over 10, and 6 times 2 over 10, and I add them together, I'll end up getting the same answer. Okay, The reason why I've shown that is to just say that if you had a problem where you were only given the probability distribution and they asked you to find the mean, there's going to be some problems like that in the book. That would be the procedure that you would take. It says to find the mean, mu sub x, of a discrete variable x, multiply each value of the random variable by its probability. So you're just going to simply multiply straight across and then add the totals. And we get 4.1 there. Now, why would we ever want to do the calculation? Well, because if we have a distribution here, we don't have the data values in front of us. Okay, so that would really be our only option. Now, you might say that, okay, we don't know the values, but we can get the values. Like I see that I've got 0 1s, 2 2s, 1 3, 3 4s, 2 5s, and 2 6s. Yes, for this problem, you could produce the data from the fractions that are given, but we're not always going to have fractional form. Okay, sometimes we might have decimals that are rounded to a certain spot, and there is no way to know the original values in that particular situation. So the procedure that I'm describing here would be our only option. Okay, now mu sub x just means mu. Okay, the subscript notation is in the book, and they're really just using that to say that you have a random variable x, and this is a calculation that is directly related to probability. Okay. Problem 7 is where I'm recalculating, basically using the procedure that I was just talking about, where I'm going to multiply straight across, and then I'm going to add these resulting numbers, and I still end up getting the mean, which would be the same number as if I were to add the numbers that were in the data set and divide by the total. Okay. Now there's a note there saying that we're going to use the calculator for all the problems in this section when we're asked to find the mean, mu sub x, and or the standard deviation, sigma sub x. Okay. So I was going to show you how to do that on the calculator now. Problem 8, we're going to use the calculator to compute the mean, mu sub x, and the standard deviation, sigma sub x, for the distribution that we made in question 6. That's this distribution here. We already know the mean is 4.1. Okay. So if you have the 83 or 84 model, you'll want to go to the lists and enter the x values into L1 and then the probabilities into L2. When you type in a probability, it will automatically give you the number in decimal form, so 2 over 10 is 0.2, etc. After you have that, you're going to hit Stat, and then go over to Calc. And sorry, I've got this tilted because I want you to see what I'm hitting here on the calculator. We want one var stats because we only got one variable. There's 2 columns, but there's only one variable. So I need to tell the calculator to use these 2 columns. If I hit second 1, it'll say L1, and then comma, second 2. So I'm telling the calculator to use L1 and L2. If I hit enter, there's the mean is 4.1. The standard deviation is 1.37. I've got a couple more digits there, but that's how I'm getting those numbers. Okay, now on some of the 83, 84 models, you might have to type in the frequency. Where it says frequency, you'll want to hit second 2 for it to say L2. Okay, in other words, you're going to use each value L2 times, not just one time. If you have the Inspire model, I have that set up here also. So you'll want to go to Lists and Spreadsheets and then type in the values into the first column here, and then we want the probabilities on the other side. So I'm just quickly doing this. 2 over 10 is 1 over 10, and 3 over 10, 2 over 10, and then 2 over 10. It'll give you the numbers in a reduced form there. So after you got the values typed in, you'll hit Menu, and then go down to Statistics, and over to Stat Calculations. Over again, we want one variable stat, since we only got one variable x. hit enter, and I want one list there. So I'm going to say OK. Now, in the X1 list, I want it to use my first column, which is column A here for this problem. And then for the frequency list, I'm going to type in B with these brackets. So it's going to use each number in A, B times. It'll give the answer in column C. Hit enter, and there's our results. So there's the mean is 4.1, the standard deviation 1.3748 is what I was getting here also. Okay. Problem 9 is another example. The Stanley Cup is a best-of-7 series to determine the champion of the National Hockey League. The frequency distribution represents the number of games played, X, in the Stanley Cup before a champion was determined from 1939 to 2017. Okay, and there was no champion in 2005 because the season was canceled. All right, in part A, we want to construct a probability distribution for the random variable X. So here's our frequency distribution. Of course, the 78 here would represent the number of games played from 1939 to 2017, disregarding 2005. So that would be my total in the sample space. If you take each frequency divided by the total, you'll get the probabilities here. I've rounded all 4 of these to 4 digits. I wouldn't care if you rounded to 3 digits or whatever. You know, I guess my math lab would be telling you where to round. But this would be another discrete variable, right? So we're going to only have counting number values. In other words, it might take only 4 games to determine a champion in a best-of-7 series. It might take 5, it might take 6, or it might take all 7 games to determine the champion in a best-of-7 series. So this table would be my answer to part A. Part B, use your calculator to compute the mean and the standard deviation for the random variable X. Okay, so I'll just quick type this in here into the, I'll use the 83 model here. So I need to clear out L1 and L2. And L1, I'm going to use 4, 5, 6, and 7 as the values. And L2, I'll just use the rounded decimals here, which were 0.2564, and then 0.2308, 0.3077, and then 0.2051. If you were to use the fractional form, that would be fine also. It's not going to affect the answers here in what we have. So then you'll hit Stat, go over to Calc. We want 1 var stats, and then I'm going to hit second 1, comma, second 2, since I'm telling the calculator to use these 2 columns here. And the mean is 5.46, roughly, if you round. And then the standard deviation is 1.08. So the interpretation of this would be to say that on average, we would expect the Stanley Cup playoff to require about 5.46 games to determine the champion. Okay. The standard deviation is 1.08. Of course, the standard deviation represents how spread out the numbers are. This is not a big spread. Only, a little bit more than 1 unit away from 5.5. So, while the average is 5.46 roughly, it wouldn't be unusual for the series to take 4 games or 6 games or 7 games, since all 3 of those numbers are roughly 1.08 units away from 5.46. Okay. That's the end of section 6.1. The homework is on page 305. Be sure to look at those problems when you get a chance.